Hi, and welcome back. We're on segment 2 of lecture 14 on analysis of variance. And in this segment, we will step through a one-way between groups analysis of variance. The example I'm going to use for this segment takes us back to the first week of this course, where I talked about the idea of training your working memory to enhance intelligence. And if you remember, this paper was published by Yaki et al. In 2008, where the independent variable was the number of training sessions that each individual subject performed. So again, to be clear, subjects came to this lab at the University of Michigan, and the experimenters randomly assigned them to one of 4 training conditions. That is, 8 days of training, 12 days of training, 17 or 19 days of training. The dependent variable, there's a couple ways to look at it. One is they had subjects perform an intelligence test before and after training. So just for ease of demonstration, and so we can do a one-way between groups ANOVA, what I'm doing here is using the gain score as the dependent variable. So just their score on the intelligence test after training minus their score on the intelligence test before training. So just post minus pre. This is what the data frame would look like if we were working in R. So just to be clear, we would have subject number in the first column, then what condition they were in, how many training sessions were they in, their pre-score, their post-score, and their gain score, which is just the difference. In this lecture, what I'd like to do is actually do a one-way ANOVA by hand. So I'm going to set up the data this way. This is not how it would look if you were working in any statistics software package, and it's not how it would look in R, and you'll see that in an upcoming lecture where we do analysis of variance in R. But just to show you the data, again, I just made up data to be consistent with their results. I'm presenting it this way. This is easier for doing hand calculations, if you will. So let's just assume there were 5 subjects in each of the 4 conditions. So 20 subjects total came to the lab. We randomly assigned them to one of these 4 conditions, and these are their gain scores. So if you just eyeball it, you'll see that people didn't gain much if they only did 8 days of training. They gained a little more if they did 12, and so on. So we could do a one-way analysis of variance to analyze these data to ask the question, is there a significant difference across those 4 groups of subjects? That is, does training enhance intelligence? And that's the hypothesis under investigation. The way to do that is to calculate an F ratio. And the F ratio, you can think about it a few different ways. One way I really like to conceptually think about it is just systematic variance relative to unsystematic variance. Remember, the t-test was a deviation score, that is the difference between 2 means, so like mean 1 minus mean 2, over standard error of the difference. That was how much of a difference did we observe relative to how much of a difference did we expect due to chance. The F ratio is exactly the same. It's, I should say, analogous to, in the same way, except now instead of dealing with deviation scores, we're dealing with variance. So just square everything. Now we have variance over variance, and it's just systematic variance. How much variance did we create with the introduction of our independent variable relative to just how much variance do we observe just due to chance? And the really cool thing about analysis of variance is that is easily calculated by just looking at the between groups variance relative to the within groups variance. So I might rewrite that as mean squares between over mean squares within, but the notation scheme I prefer, and this comes from Keppel and Wicken's textbook, which is an excellent textbook, is mean squares sub A over mean squares S within A. The way to read that last term is subjects within groups. So A refers to groups, S refers to subjects. So the F ratio I can write as MS sub A over MS S with an A, and then mean squares, again, is always just sums of squares over degrees of freedom. The trick is calculating the sums of squares. So here's the sums of squares between groups. What we want to know is how much are the group means varying from each other. The way to do that is to take each individual group mean and compare it to the grand mean, or the overall mean from the experiment. So I'm going to take each individual group mean and compare it to the grand mean. I'll get those deviation scores, I'll square them, I'll sum them, sums of squares, and then divide by the number of groups minus 1, and that will give me mean squares. I also need to pre-multiply by the number of subjects in each group. The way to think about this is each individual subject is contributing a deviation score to both the between group sums of squares and the within group sums of squares. So how to calculate the within group sums of squares? I just take each individual subject within a condition and compare them to their group mean. That's error variance or unsystematic variance. Why are people in the same condition, the people who are treated exactly the same, they went through the same exact amount of training, why are they differing from each other? I don't know. That's unsystematic. That's just chance error. So our estimate of the average amount of chance error, like standard error in the t-test, is calculated this way, just by looking at each individual, how much they differ from the other individuals in their same condition or group. Degrees of freedom is always the number of scores that go into that variance term minus 1. So for A, df sub A, it's just the number of levels of the independent variable, A minus 1. In this case, 4 minus 1, or 3. Degrees of freedom S within A is how many subjects are in each condition, or each group, minus 1 times the number of conditions. And df total is the sum of dfa and dfs within A, and it's the total number of subjects minus 1. What's common in an analysis of variance is to summarize all of those numbers in an ANOVA summary table, where you list the source of the variance, the between groups, the within groups, and total. And here I've just summarized all the formulas we just looked at. So to make these more clear, we're going to walk through this example and actually do all the calculations by hand. Again, I've been teaching this course a long time, and this is one place where students tell me it really helped conceptually to walk through and do an ANOVA by hand just once. Again, we'll do this once, and then in an upcoming lecture we'll do it in R. Okay, so again, to go back to the summary table, let's start here with sums of squares between groups. Then we'll do sums of squares within groups. That's the hardest part. Once we've got that, it's all just simple algebra to get the degrees of freedom, to get the mean squares, to get the F ratio. Okay, so here's sums of squares between groups. Again, I just want to take each group mean and compare it to the grand mean. So there were 4 groups. The mean of the first group was 1. The mean of the second group was 2. Mean of the third group, 4. Mean of the fourth group, 5. The overall mean was 3. 3, 3, 3, 3. So what I'm doing is getting each deviation score, but I'm comparing groups to grand mean. I square all those, I sum them, that's my sums of squares. And remember, I have to pre-multiply by little n, where little n is the number of subjects within a group. Because again, each subject is contributing a deviation score. So the sum in here is 10, pre-multiply that by 5, I get 50. Here's the sums of squares within groups. And again, the group means were 1, 2, 4, and 5. These scores are the individual subject scores within a group. So to do the first group, that's the top row, I calculate their within group sums of squares by just taking each individual subject score, comparing it to their group mean. Do it for the second group, third group, fourth group, so each row represents a group. Sum that, and I get 26. Degrees of freedom, as I said, real easy, is just 4 minus 1 for the between groups, little n minus 1, because there are 5 people in each group, minus 1, 4 times 4 groups is 16. Mean squares is just sums of squares over degrees of freedom. And the F is the ratio of the mean squares. So it's 16 over 1.6. We get an F ratio of 10. It's a big F ratio. I don't even need to look at the degrees of freedom to know that that's significant. But remember, the F ratio, the F test, has a family of F distributions that we need to look at to get the right p-value, just like the t-test has a family of t-distributions. It depends on the number of groups and the number of subjects within a group. But in this case, the p-value is really low. It's 0.0005. And I would reject the null hypothesis. Again, where exactly does that p-value come from? It comes from these sampling distributions. And the difference between these curves is just how many groups did we have and how many subjects did we have. This is the family of F distributions, like the family of T distributions. And that's when I said, the F is 10, I know it's significant, because look out here at the end of this graph, this is an F of 2 right here. So 10, is way out here. I know that the percentage or area under the curve is really low. It was 0.001, right? So it's significant. We reject the null hypothesis. The difference between those groups is statistically significant. Of course, there's a few more things we want to do. Just like when we did a t-test, we want to calculate effect size. And there's an extra step here, is we need to do what's called post hoc tests. So we know that the manipulation of number of training sessions was significant, but we don't know, was there a significant difference between the first group and the second group, the second and the third, and so on. So we'll calculate effect size, and we also need to do post hoc tests. So the way to calculate effect size in analysis of variance is by calculating eta squared. So that's this guy right here is eta squared. And it's the same exact statistic as R squared from multiple regression. It's just the percentage of variance explained in the outcome variable. Or now I'm going to use the phrase dependent variable. So it's just what's the sums of squares associated with our treatment, A, divided by the total sums of squares. In our case, it's really large, and this is unusual. Again, I just made up the data. We only had 5 subjects per condition. I made the between groups variance really big. So we get a really large eta squared. It's 0.66. That's, typically see that in real research, but that's our eta squared in this example. There are several assumptions we make when we do analysis of variance. One, again, we're still dealing with an outcome variable or dependent variable that's continuous and has a normal distribution, or relatively normal. And there's a new assumption in here called the homogeneity of variance assumption. And the idea behind that is we're assuming that within each group there's an equivalent amount of just unsystematic variance. And that's a really important assumption. Because if I go back to the calculation of mean squares S with an A, or sums of squares S with an A, what I've done here is I've just put all of this together. So the first row is the first group, second row is the second, and so on. And then we just sum that all up and we divide it by the number of groups. So we're averaging across 4 groups. we're making the assumption there that each group is contributing sort of an equal amount to that error variance. If they're not, then that's not representative of the four groups, right? Let's go back to like descriptive statistics and our ideas of representative measures of central tendency. So if that's not the case, then I can't assume that I have homogeneity of variance, and I shouldn't be doing a one-way ANOVA. So in the lecture where we do analysis of variance in R, I'll show you how to test this assumption by doing what's called Levene's test. And if we don't have homogeneity of variance, if we violate that assumption, then we'll just conduct maybe just simple t-tests using what's called a restricted error term, restricted to the groups that are under comparison. So that's everything I just said there, and we'll see more about that in lecture 15.